Hey guys, welcome to this video where I'll be doing some fluid dynamics practice problems. I'm going to do two free response problems just to go over some of the major concepts from the past three videos over fluid dynamics. So let's get started. Alright, so let's look at our first question here. Now what I suggest you do is pause the video and read through the question, try to answer it yourself first, then you can come back here and watch the solution. Another thing to think about before you answer the question is what topic is it trying to test, right? They're only testing, there's a finite number of fluid mechanics topics that we've covered. And so this test is only going to be testing you on things that you've learned. Now they may extrapolate a few things, but you can always find some grounding in a topic that we've discussed. All right, so that's something that you should look for in the question. So let's read through it first. It says a fluid flows from left to right through the constant depth channel shown below in an overhead view. A grid has been added to facilitate measurement. The fluid's flow speed at A is 2 meters per second. Assume a 1 by 1 meter grid. It's saying for A, shade in squares to represent the water that has flowed past point A in the last 2 seconds. All right, so what's key on here is that it's saying 2 seconds. So it's going 2 meters every second. So that means after 2 seconds, it should have gone 4 linear meters. Okay, so that means that we need to color in up from a 4 meters worth. And remember, the pipe is full of water, so it's going to be 8 blocks. Okay, so 8 little blocks there. And then for B, it says shade in squares to represent the water that has flowed past point B in the last 2 seconds. Explain. All right, so we know that according to our continuity equation, A1V1 equals A2V2, we can see that B has a greater area or dimension of pipe. It doesn't matter if it's round or rectangular. We're not really concerned with that. We just know that it's bigger. And so when it's bigger, the speed will have decreased. So this one should be flowing at a slower speed, which we know automatically. And we also see that it's doubled in size, right? So if it was 2 blocks thick, now it's 4 blocks thick. And so that means that it should be half the speed. But even if you kind of were confused about that portion, you should say that within 2 seconds it covered 8 blocks worth of water. So by conservation of matter, 8 blocks of water has to have been over here as well. So we have those 4 and then the next 4. And then that shows that it's traveling 1 meter every second. So for 2 seconds, it's past 2 meters. Okay, so you can see it's definitely moving slower than it was at A. Then part C says shade in squares to represent the water that has flowed past point C in the last 2 seconds. Explain. So again, we're just needing 8 blocks, and we also need to make sure that it makes sense, right? So in this case over here, this is even smaller than A, so it should be moving faster. So I should still color in 8 blocks. So we're going to do 1, 2, 3, 4, 5, 6, 7, 8. And then I'll just kind of shade in the whole region. Okay, so that would mean that it's moving at 8 meters, or 4 meters, sorry, per second. Okay, so if that's in 2 seconds and there's 8 blocks, then that means it was traveling at 4 meters per second. So the explanation for B and C are really the same thing. We could say due to conservation of matter, 4 blocks worth of water has to pass in the same or given amount of time. We could also say that due to the size or change of the area, cross-sectional area of the pipe, the speed must adjust inversely. So where the area is smaller, the speed must be higher proportionally. All right, so let's move on to the last part of this question. All right, so part D says, for the same pipe, a top and side view is shown below. The liquid level is shown for pipe A. which is open at the top, but not shown for pipes B and C. Draw an appropriate level of liquid in pipes B and C to indicate the fluid pressures at those points. Explain your drawing. All right, so we can see that we have to now apply conservation of energy. Whereas we just applied conservation of matter, now we're applying conservation of energy. So if we use the Bernoulli equation, the basic foundation we have to worry about is that we know that pressure and velocity are inversely proportional to one another. So where the velocity is higher, the pressure is lower. And where the velocity is the slowest, the pressure would be the highest. So that means that the velocity was slowest at location B, so it should have the greatest pressure. And if the fluid pressure from the bottom is pushing up harder than in the other locations, it should have the highest water level. So we will color that in all the way to the top. A would be the medium. It's the second slowest place, or second fastest place, and then the fastest place at C should have the lowest pressure. And so we should just color in maybe just about half of what's in A. All right, so question A dealt with, or A, B, and C dealt with conservation of matter, and this question and the continuity equation. And then question D dealt with conservation of energy and the Bernoulli equation. Let's move on to the next question. All right, this next question says a pump submerged at the bottom of a well that is 35 meters deep is used to pump water uphill to a house that is 50 meters above the top of the well as shown above. The density of water is 1,000 kilograms per meter cubed. All pressures are gauge pressures. Neglect the effects of friction, turbulence, and viscosity. Part A. Residents of the house use 0.35 cubic meters of water per day. The day's pumping is completed in 2 hours during the day. I, calculate the minimum work required to pump the water used per day. And 2, calculate the minimum power rating of the pump. Okay, the first thing to note is that little I and double I, they are not really questions that are specific to fluids. They're more sort of mechanics-based questions. So just keep that in mind if you kind of forgot some of that stuff. But we have talked about work and all of that, so you should hopefully be able to remember this. Okay, so let's write out a few ideas here. So the first thing, calculate the minimum work required to pump the water used per day. Now remember, work has no relationship to time, so the time has nothing to do with little I. Okay, so let's start by saying that the work needed to raise the water from the well up to the house is F times delta, and I'm going to use delta Y here instead of delta X because of vertical displacement. This would be the force would be the weight of the water times the Y displacement. And then because we're dealing with densities and volumes here and we don't really have mass, we're going to use the substitution rho times volume to substitute in for m. So when everything's said and done, we should be plugging in rho times v times g times what I'm going to put here is height rather than delta y. Okay, so then we just need to plug in some values. So let's go ahead and scoot this up here. And we're going to plug in our values here. So we have the density of the water is 1,000 kilograms per cubic meter. And then we're going to be multiplying that by the volume of 0.35 cubic meters. Then we're multiplying by G, which I'm just using 10. And then the height that it's moving is 35 plus 50. So 85 meters. Okay. And then if we multiply all of that, we get 297,500 joules. All right. So that would be the amount of work needed for the pump to raise the water throughout the day. The next part then says calculate the minimum power rating of the pump. For the power, so let's just go ahead and get rid of some of this stuff over here. Power is going to be work divided by time. So we're going to say we just calculated the amount of work done, and this would be powers measured in joules per second for the unit of a watt. So we're going to take our 297,500, and I'm not using significant figures here, just FYI. And then this is going to be in 2 hours. So if we want to convert the hours to seconds, we're going to say 2 hours times 60 minutes per hour. And then we'll do 60 seconds per 1 minute. All right, and then we get minutes and hours to cancel. So we have 2 times 60 times 60, and that will give us 7,200. And then that answer becomes 41 approximately. And that's 41 watts. All right, so here we have the second part. It says the average pressure the pump actually produces is 9.2 times 10 to the 5th pascals. Within the well, the water flows at 0.5 meters per second, and the pipe has a diameter of 3 centimeters. At the house, the pipe diameter is 1.25 centimeters. Calculate the flow velocity when a faucet in the house is open. So when I'm thinking about this and I'm trying to connect it to concepts and ideas that we've already talked about, that's going to be the following, right? We know that the pipe diameter is changing from there to there. And of course, the speed's going to have to change. Now, we just talked about this in the previous question. We're going to use the continuity equation, A1 times V1 equals A2 times V2. All right. And then we're going to substitute in what we have. So to get the area at the bottom there, first I need to convert into meters. That's huge. So I'm going to do pi r squared, right? And they gave me a diameter, so that's actually going to be pi times 0.03 divided by 2, and that's squared. So that's my pi r squared for the bottom. And then the speed at the bottom is 0.5. So I've got everything there on the left-hand side. I'm just going to shrink this down, kind of fit it in there. Took the question with it. All right, and then on the second part, I'm going to do the same thing for the area, but with the new diameter measurement, which was 0.0125 divided by 2 squared, and that's going to be times the unknown value that I'm looking for. And so after doing all the math, I get that V2 is equal to 2.88 meters per second, or something close to that. All right, so continuity equation. All right, let's take a look at the second part here. It says explain how you would calculate the minimum pressure in the faucet. Okay, so they didn't actually ask you to physically calculate it, but just to explain it. So what I would use, though, to get the pressure at the top is I would be using this equation, right? And the reason that I would have to use this is because so many different things are changing, right? Now, we know that there's a constant amount of energy in the pipe, in the fluid, but the height's changing, the pressures are changing, the speed's changing. So there's a lot of changes, and this equation tracks everything, right? So what we can plug in here, and I'm going to do the numbers, even though they're not asking for it, just because I think it's an important thing to compare. So one thing that's really important is this Y1 position and the Y2 position. So for Y1, I could either put negative 35, and for Y2, I could put 50, because remember, the difference between Y2 and Y1 needs to be 85. So if I were to add this whole term to this side of the equation, because I could add those two like terms, then that would give me 85, because I would be adding it to that side. Okay, so just keep that in mind. You can do it in many different ways, or you could put Y1 as 0 and Y2 as 85. So just think through the process of what's most important. Okay, so let me get rid of some of that mess. And then we're looking at here, they gave us, so we know the density of water, that's 1,000. So in every term that has that, we've got it. We know the velocity down at the bottom. We also know the velocity at the top now. We know the y positions. We know the g's. And they also gave us pressure 1 at the bottom. And so there we can see that we can solve for pressure 2, which would be at the top. So in terms of explaining how we would calculate, what I would say is we could use Bernoulli's equation as a statement of conservation of energy, assuming that everything with a subscript of 1 or everything on the left of the equation has to do with down at the bottom in the well, and everything with a subscript of 2 or on the right side of the equation has to do with everything at the house, then I can plug all known values in and calculate P2 using conservation of energy. All right, I hope that helped you guys. And the next set of videos, we're actually going to enter into a new area, thermodynamics.